Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on graph theory, lecture number 36, in which I will discuss on planar graphs, map and region. Firstly, we want to know what is planar graph? A graph which is drawn on a plane so that no edges intersect with each other except at vertices. For example, let we have a graph. Here V1, V2, V3, V4 be the vertices of the graph and edges are E1, E2, E3, E4. Another edge is here E5. Here we see that this graph is drawn on the plane and no edges intersect with each other except at the vertices. Here at the point of vertex V4, E4, E5 and E1 edges will intersect. But except the point of vertices, no edges intersect here. If we draw another edge, this is E6, then the edge E5 and E6 will intersect with each other. So this type of graph will not be a planar graph. If we draw the same graph in another way, here vertex V1, V2, V3, V4, E1, E2, E3, E4 and this is edge E5. If in place of E6, if we draw the edge like this is E6. Here we see that no edges intersect except at the point of vertices. This is a planar graph. The second graph is embedding of the first graph. Now we define the planar graph. A graph G is said to be planar if the graph can be drawn in a plane so that its edges do not cross with each other except at vertices. A drawing of planar graph G on a plane such that no edges intersect is called embedding of graph G. Let we have a complete graph with 4 vertices, which is usually represented by the following figure. This is figure 1. Here we have vertices V1, V2, V3, V4 and edges are E1, E2, E3, E4, E5 and E6. Here edges E5 and E6 cross with each other. Here, that is, they intersect with each other. We may draw the graph of the figure 1 with non-crossing of edges as follow. We get figure 2 and figure 3. In figure 2, we see that we have taken the edge E5 outside this figure connecting V4 and V2, and other vertices and edges remain in the same position. In the figure 3, here we see that V1, V2, V3 be vertices. We take V1, V2, V3 vertices and we take vertex V4 inside this triangle and we connect with V1, V4, V2, V4, V3, V4. And the name of the edges will be the same as it was in figure 1. Here we see that edge connecting V1 and V2 is E1. Here also connecting vertices V1 and V2 be edge E1. Here edge connecting vertices V2 and V3 be E2. Here also be same. Edge connecting V2 and V3 be E2. Similarly, edge connecting V3 and V4 is E3. Edge connecting V3 and V4 is E3. Here edge connecting V4 and V1 is E4. Here edge connecting V4 and V1 is E4. And edge connecting V2 and V4. V2 and V4 is E5. Here also edge connecting V2 and V4 is E5. Here edge connecting V1 and V3 is E6. Here edge connecting V1 and V3 is E6. So we have drawn the figure 1 as planar graphs. Figure 2 and figure 3, the relative position of vertices and edges remain same. So these graphs are called planar embedding of figure 1. Now we define non-planar graph. A graph G that cannot be drawn on a plane without crossing its edges is called non-planar. Now we define map. A particular planar representation of a finite planar graph is called a map. We say that map is connected if the graph is connected. Now we define region. A given map divides the plane into various areas. A region of a planar graph or map is an area of the plane that is bounded by edges and is not further divided into sub-areas. For example, here we have graph G. This is a planar graph. The planar representation of this graph is called a map. Here we see that the map is divided into various areas. Here this area bounded by V1, V4, V2. This area is called R1. This area is called R2. This area is called R3. This area is called R4 and outside R5. This particular area R1 is not further divided into sub-areas. A region is finite if the area it encloses is finite. Otherwise, it is called infinite. Here, this region R5 is infinite because area encloses be outside of this map. This graph has 6 vertices and 9 edges. The graph is divided into 5 regions: R1, R2, R3, R4 and R5 respectively. We see that 4 regions are bounded. R1 is bounded, R2 is bounded, R3 is bounded, R4 is bounded. But R5, fifth region, is not bounded, it is unbounded. Each region of a map consists of edge bordering it. Here we see this particular region R1. Here we see that the edges V1, V4, V4, V2 and V2, V1 border this region. Similarly, other regions are also bordered by edges. Sometimes these edges will form a cycle or sometimes not. Here for region R1, here we see that the edges bordering it form a cycle. Similarly, R2, R4 and R5. But in the case of R3, the edges bordering it do not make cycle but a close walk. This close walk moving counterclockwise, as here we start from V3, then V4, then V5, then V6, then again we return back to V5, then V3. This is a closed walk. The region R3 is not bounded by cycle. The region R3 is formed by the closed walk. Here we see that edge V5, V6 occur twice for making closed walk. Now we define degree of a region. By degree of a region R, we mean the length of the cycle or length of the closed walk which border the region R. Here we see that this is region R1. Here the border is a cycle and border is formed by 3 edges: V1, V4, V4, V2 and V2, V1. So the degree of R1 equal to 3. Now here region is R2. The border is a cycle and the edges are V3, V2, V2, V4 and V4, V3. 3 edges border the region R2. So the degree of R2 is 3. Here degree of R3. Here region R3 is not made by the cycle. It is made by a closed walk. Here for closed walk we have edges V3, V4, 1, V4, V5, 2, V5, V6, 3, V6, V5, 4 and V5, V3, 5. So degree of R3 is 5. Degree of R4, the region R4 is formed by cycle and edges are V4, V1, 1, V1 and V2, 2, V2, V3, 3, V3, V5, 4 edges are in border of R4. So degree of R4 is 4. Now degree of R5 is infinite region, but we take the border V5, V1 as one edge, V1 and V4 second edge, and V4 and V5 third edge. So degree of R5 is 3. A region R of planar graph G can have degree 1 if its border is a loop. If this is vertex V and this is loop, here region is R. This region R is formed by one edge in the border. So the degree of this region is 1. Therefore, degree of region R can have degree 1 if its border is a loop. A region R of planar graph G can have degree 2 if its border is formed by parallel edge, like this. Here edges are E1 and E2, vertices V1 and V2. Here this region R. Here number of edges in border B2. So a region R of G can have degree 2 if its border is formed by parallel edges E1 and E2. Otherwise, every region must have degree 3 or more. Now we prove a theorem. Theorem is a planar graph can be embedded in a plane such that any specified region can be made the infinite region. Now we prove this. Let we have following planar representation of graph G. This is planar representation of the graph G. Here we have vertices V1, V2, V3, V4. Edges are E1, E2, E3, E4, E5 and outside E6. Regions are, this is R1, R2, R3 and R4. In this planar representation, infinite region is R4, characterized by edges E1, E2 and E6. We wish to make the finite region R1 characterized by edges E1, E3 and E4 as infinite region. So now we redraw the graph as follows. This is our new embedding. Here we see that the relative position of vertices and edges are in the same position. Here we see that the region R1 characterized by the set E1, E3 and E4. Here also the region R1 was characterized by the set E1, E3, E4. Here also be same, but here R1 region is infinite. Now we prove the next theorem. Theorem is prove that the sum of degrees of regions of a planar graph is twice the number of edges. Now we prove this. Since from the definition of degree of a region, we know that by degree of a region, we mean the length of the cycle or closed walk which borders the region. Therefore, each edge either borders the two regions, or if it is contained in a region, then it will occur twice to form a closed walk along the border of the region. For example, this is the planar representation of the graph G. Here we see that vertices are A, B, C, D, E, F, and regions are R1, R2, R3, R4, R5. Here we see that the edge AB is on the border of the region R1 and R4. When we find the degree of R1, we take edge AD1, edge DB2, edge BA3. So this is 3. Here edge BA has contributed 1 degree for region R1. Again, when we find the degree of R4, here we see that for finding the length of the cycle, we count the edges which are in the border of the region. Here we see AB 1 edge, BC second, CE third, and EA fourth. Degree of region 4 R4 is 4, but here also we have taken the edge AB. Here we have taken edge AB. Also here we have taken edge AB. So any edge is taken twice for finding the degree of the regions. If it is in the border of two regions, but here we see that EF be an edge which is not in the border of two regions, but it is contained in a region. So when we find the degree of region R3, we count the edges for closed walk. Here DE1, EF2, FE3, EC 4 and CD 5. Here we have taken EF twice. If an edge is not in the border of two regions, but it is contained in a region, then in that case we take this edge as twice for finding the degree of the region. So in each cases we see that each edge contributes 2 degree to the regions. So total sum of degrees of regions is equal to twice the number of total edges. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.